Hello everyone, welcome back to the video. So today we are going to see problem number 2749, minimum operations to make the integer 0. Okay, so before starting, I will give you just an overview of this problem. It's not going to be easy, okay, and it is not a problem that will come to your mind, the solution come to your mind, okay. So pay attention, I will try to explain you, okay, and let's read the problem and understand it. So you are given two integer num1, num2, okay. In one operation, you can choose integer I in the range of 0 to 60 and subtract 2 raised to I plus num2 from num1. Okay, so just now focus on this part, 2 raised to I, okay, from 0 to 60. So don't you think it's like a bit manipulation, because 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. These are all binary representation, correct? So I think this will be a bit manipulation problem. Okay, first thing we can identify that. The second part is we're going to subtract the num2 that is given, so that is normal. Okay, let's understand what we need to find. Return the integer denoting the minimum number of operations needed to make num1 equal to 0. So we need to find how we can make num1 equal to 0 with doing these operations and how many operations are needed repeatedly. If it is possible to make num1 equal to 0, return -1. So if it's impossible, so we need to return -1 in that case. Okay, so let's read one problem example here. So num1 equal to 3 and num2 equal to -2. So the answer is 3 here, and we'll read here. So I equal to 2 and subtract 2 raised to 2 plus -2. Okay, so this equation 3, which is our num1, -4, 2 raised to 2 is 4, and -2 our num2 will give us 1. Now again from 1 we are subtracting the same 2 raised to 2 plus -2. Okay, we'll get -1. And in next case we are taking 2 raised to 0. Okay, so you can see -1 and we're getting a 0. So this is an easy, this is simple to understand. Okay, and 5 and 7 they've written -1, that we cannot, it is impossible to make 5 as 0. Yeah. Okay, so I'll just take this part and we'll go here. Okay, so okay, so input is 3 and num of 2 is -2. Okay, so okay, well, let's do one thing. I'll just remove this part just so that we can see the problem. Okay, I'll take a pen. Okay, so first I will write some bits. Okay, 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and 2 raised to 4. Okay, so this will be 1, 2, 4, 8, 16. Okay, we can write till 60, but no needed as of now because number is 3, a smaller number. So we need to find the operations needed to make 3 equal to 0. Okay, so and we need to minus two components from that. First component is 2 raised to I or something I. Okay, plus the second component is num of 2, okay, into the number of operations. I will write O for it, OP. Okay, number of operations. Okay, so let us do one thing. From this I will do 3 minus n2, num of 2 is -2, into num of operations. Okay, okay, then I will keep this part as remaining. Okay, we'll check this later. So if I do iteratively from, suppose operation I take operation I took as 1, okay, and I will go from 1 to n number of operations. Okay, and I will try to find it, like if it's possible to make it 0 or not for every operations. Okay, that I can do. Okay, so I don't recommend you, this will come intuitively to you guys, but this is how we need to solve it. So I'm trying to explain you. Okay, so first part is this. Okay, so let's make some, so suppose operation is 1, so what will be this value? 3 minus -2. it will be 3 minus 5. Okay, when operation are 2, what will be this value? This value will be 7. Okay, when operations are 3, this value will be 3 to the 6, 6, 9. Okay, these are operations value. Now we need to check if that remaining, this 5, this 7 and 9, we can make with power of 2's. Okay, we need to check that it is achievable to make this with power of 2's in k operations, means in operations actually. So how many number of bits are set, we will see for this. Okay, so now this component is remaining, right? I will change the pen color. This component is remaining, so we need to achieve this component actually. We can check like if it's achievable or not, then only we can say this operations will give us a 0. Okay, how I will explain it. Okay, just be with me as of now. So this 5 is there. 5 have how many? 2. This has 3, 3 bit set. Okay, and 9 also have 2 bit set. Okay, 9 have 2 bit set, 7 have all bit set. Okay, so here k is 1. As 2 raised to 1 we can achieve this. No, here 2 bits are set, so this is wrong. Then here we have 2 bits, we can use any 2 bits. Okay, because we can use 2 raised to I, any 2 raised to I. So here we have k equal to, we are doing operations as 2, right? So we can use 2 raised to I 2 times, and I can be anything. Okay, but here if you see we have 3 bit set, so we cannot make the count 3 anyhow in this case, so this is also wrong. Now here we have 3 operations, means we can choose the 2 raised to I 3 times, and we only want 2 bit set, so we can do that. Okay, one time we can choose 2 raised to 0, one time we can choose 2 raised to 1, and other time we can choose 2 raised to 3. Okay, so in that way we can do it. 2 raised to, sorry, 2 raised to 2 and 2 raised to 1 we can do it. So we want to make 9, right? So 9 is possible. I will tell you how. I will just erase this. Okay, so the first part is clear, I think. Okay, so we'll do 3 equal to, so the formula is this: 3 equal to number of operations OP into 2 raised to I plus number of operations into num2. Okay, so we will see here. So the answer is 3. We know that here it is given. So 3 into minus 2. What it will be? 3 into minus 2? It will be 3 to the 6 minus 6. I'll just remove this. Okay, it will be minus 6. Okay, here it will be 3. And we see these operations in 2 raised to I. Okay, which I we don't know as of now. We'll just go there, and this equation will become, if we take this 6 here, it will become 9 equal to operations of 2 raised to I. Okay, we have the operations number, it is 3. 3 into 2 raised to I. So sum of 3 power of I, like that it is. So we just need to check if we can make 9 with this 3 power of I, like 2 raised to I plus 2 raised to I plus 2 raised to I. Okay, equal to 9. So we need to check like we can make this equation correct. Okay, so 9, can we make it with this? Yeah, we can make it. So I will show you how we can. So here it is 1, here it is 1, so 8 plus 1 it is 9. So how we can do it? We can take this 2 raised to 0. Okay, we can take 4, 8. So we can take, instead of 3 we can take 2, 1. So we can take 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2. So if we just add this part, it is 1 plus 2 plus 4. And if you add this, what it will get? We'll get a 9. Okay. So hope you got it, how we are going to solve it. I'll try to explain one more example for this. Okay. Let's go with another example. Let's take 11 and num equal to 2. This is positive 2 and this is 11 is our num1. Okay. So 11 equal to number of operations into 2 raised to I plus number of operations into 2. Okay, so this is the our logic that we built. This is one equation that we created. Now we will replace this number of operations from, we'll start enumerating from 1 to till we get the answer. Okay, so suppose I give 1 here, 1 into 2 minus 11, and so let's try for 1 first. Okay, so if I give here 1, so 11 minus 2 equal to 2 raised to I. So 11 minus 2 will be 9 equal to 2 raised to I. Can we get 9 from just 2 raised to I somehow? Like here we have 1, 2, 4, 8, correct? We can get exactly 9? No. So that is not correct. So our 1 will be not satisfying this. We need to take more operations. So let's take 2. 11 minus 4 equal to 2 raised to I plus 2 raised to I. So this is I am giving, it's not 1, okay? This is I. So 11 minus 4, what it is? It will be 7. Okay. Can we create a 7? Because 7 has 3-bit set and we have only 2 i's here. We cannot do that. Okay. Now we'll take the third one, like operations equal to 3. 3 2s are 6. 11 minus 6 equal to what it will be 5, and we have 3 2 raised to I. Okay, because operations are 3. So we can make 5 with these 3 2's because 5 is like this. Okay, yeah, definitely we can make it. How? I will show you. Equal to, so if we do 2 plus 2 plus 1, so 2 raised to 1 plus 2 raised to 1 plus 2 raised to 0. Okay, so this will give us 1 plus, sorry, 2 plus 2 plus 1 equal to 5. So we need to check this. So how we're going to check this? We are just going to see if the bit in this should be less than or equal to the operation number. Then we can say it's correct and we just return that number. Okay, what if where we will stop now? So we don't know, we're going to start with 1 and we keep going till n number. Okay, how we're going to stop it? So for this, if x, okay, if this number is less than k operations, if it's less than operations, then we will return -1 in that case. How? I will show you. Okay, let me erase this part. Okay, once I write the code, it will be very simple. Okay, so if I say 11 minus 6, right, it will be 5, and operations are how much? Operations are 3, correct? So if operations are greater, okay, and this is less, then there is a problem. We cannot achieve that actually, because see, the minimum number with 3 operations is 2 raised to 0 plus 2 raised to 0 plus 2 raised to 0. So it's 3, correct? So if the number is less than 3, like it's suppose 2, so we cannot achieve this with this, correct? So it should be always greater. The number which we are getting from subtracting the num2 operation into operations, it should be always greater than k, because the minimum number we can get from the k operations to means sum of the k operations for the binary 2, like 2 raised to power into k. So that will be 3, the number itself, operation itself, and we cannot get less than that. So that is why we'll write the condition like, suppose x is this one. Okay, if it's less than k, we'll return -1. Like it's not possible for us to find it. Okay, so let's go to code and write it. It's a very simple code. Okay, for int I equal to 1, we'll start from 1. Okay, we can save int I equal to 1 while true, we can say this. So we've taken this, so we'll iterate from I equal to 1, right? So I think here the constant 10 raised to 9. So we need to take a long number here. Okay, we will take a long x equal to num1 minus, we'll convert this into long, okay, I into num2. So this will give us the remainder part. Okay, now we'll do bit calculation equal to long dot bit count on x. So this will give us bit count. So if x is less than I, then we'll return -1, and if I is greater than equal to bit, then we'll return the I itself. Okay, I plus plus. So I think the code is complete. It's very simple. Let's try to run and submit it. Okay, I'll just try to submit it and see if it's working. So, okay, so you must be thinking it's very small code and so easy, right? So it's easy only. I have explained you every detail. So I'll just go once again. So here we are finding this remainder, what will be the x, and we are checking if x is less than I, because I is the smallest thing that we can make out of power of 2's. So we'll return the -1, and here we'll checking if that bit is less, then we can make the bits. Okay, so here the time complexity will be log n, okay, and space will be 1 only. Okay, hope you understand everything. If you have any doubt, please comment down. I will try to help you. Thank you.